In this lecture, I'll give you an overview of IPv4 address exhaustion and network address translation, that's NAT. Now, a lot of what we're going to cover here was already spoken about back in the subnetting section, but that was a while back, so I'll give you a quick review again here. First up, our RFC 1918 private addresses. The IETF documents standards with RFCs, and RFC 1918 specifies private IP address ranges which are not routable on the public internet. So if you send traffic with a destination address, which is a private IP address, out to the internet, then the service provider routers will just drop that traffic. Private addresses were originally designed for hosts which should have no internet connectivity. For example, maybe it's a university and they need to have connectivity between the hosts internally, but they don't want the students to have any internet access. Public IP addresses cost money. And if an organization has a part of their network where the hosts need to communicate with each other over IP, but they don't need outside connectivity to the internet, then they can assign those hosts private IP addresses. There is a range of private addresses in each address class, A, B, and C. Our range in class A is 10.0.0.0 to 10.255.255.255, which can also be written as 10.0.0.0/8. The range in class B is 172.16.0.0 to 172.31.255.255. That can be written as 172.16.0.0/12. And the range in class C is 192.168.0.0 to 192.168.255.255. That's 192.168.0.0/16. So the class A range of 10.0.0.0/8 and the class C range of 192.168.0.0/16, they're dead easy to remember. The one to commit to memory is the class B range, which is 172.16.0.0 to 172.31.255.255. Now, the designers of IPv4 did not envision the explosive growth of its use, and 4.3 billion addresses seemed more than enough. They didn't know that everybody would be wanting to get on the internet, and not just with one device, but with their laptop, their mobile, their tablet, etc. And that's just personal users. We've also got all the business users as well. So 4.3 billion addresses seemed like it was going to be more than enough, but of course it wasn't. Also, that 4.3 billion addresses, that's just a theoretical limit. It doesn't actually get anywhere near that with the usable addresses, because the protocol is not particularly efficient in its use of the available space, and many of those addresses are wasted. The Internet Authority started to predict address exhaustion in the late 1980s, and IPv6 was developed in the 90s as the long-term solution to this problem. IPv6 uses a 128-bit address compared to IPv4's 32-bit address. So the address is 4 times as long when you write it down, but it's not just a 4 times bigger address space. IPv6 actually provides more than 7.9 times 10 to the power of 28 times as many addresses as IPv4. So way more addresses than are available in IPv4. And the idea is that the IPv6 address space will never run out. But a problem is that there's not a seamless migration path from IPv4 to IPv6. IPv6 is not backwards compatible with IPv4, so there's not an easy way to change from one to the other. So NAT, Network Address Translation, was implemented as a temporary workaround to mitigate the lack of IPv4 addresses until organizations had time to migrate to IPv6. So the original idea with using NAT for this was that it was just going to be temporary until everybody had time to change to IPv6, but it's actually turned out to be more of a long-term solution in the real world. An organization can use private IP addresses on their inside network when they're using NAT, but still grant their hosts internet access by translating them to their outside public IP addresses. That's the translation. Many hosts on the inside can share a few or a single public IP addresses on the outside. So let's look and see how that works. So we've got Office A, which is actually at Company A on the left, and Office B at Company B on the right. And you can see that both companies are using the same private IP addresses. They're using 192.168.10.0/24. That's not a problem. There's no conflict, because the private IP addresses are just used on the inside. They're not used for traffic when it's going between the companies on the outside. You can also see that the companies are reusing public IP addresses here as well. Company A, Office A, they've got 200 hosts on the inside, but they've only got 14 public addresses. That's the range 203.0.113.1/28. Company B, they've only got 6 addresses, 203.0.113.16/29, but they've got 100 hosts on the inside. Your public IP addresses cost money, so it's good that we don't need to pay for a public IP address for every host on the inside. Also, that wouldn't work anyway because of the lack of IPv4 addresses. So NAT solves that because we can use those private addresses on the inside, and they can share multiple, the same public IP addresses on the outside. Many industry experts predicted in the early 2000s that IPv6 would be ubiquitous within a few years, that everybody would be using it. But it hasn't actually worked out that way. Most normal enterprises today are using RFC 1918 IPv4 addresses with NAT. They're not using IPv6 at all. RFC 1918 has the security benefit of hiding inside hosts by default. They're on a private IP address. They don't have a publicly routable IP address, so it's not possible for attackers on the inside to directly connect to them from the outside. So that makes things more secure. Plus, network engineers have more experience with IPv4 than IPv6. Like I said, most places are just using IPv4 today. IPv6 is very different than IPv4, and people tend to not like change. So engineers are comfortable already working with IPv4. NAT is working great as a workaround, as a solution. So that's why the uptake of IPv6 hasn't actually been as quick as people were originally expecting. Thanks for watching. If you want to get hands-on practice with Cisco networks for free, then you can download my 400-page CCNA Lab Guide, which you can see above my head right now. Also, check out the video about my CCNA course. It's the highest rated course online. Thanks.